There is a semiconductor research firm in Toronto, Canada, called Tech Insights. These are the people that other semiconductor people trust. When a new chip lands from Apple, Samsung, Nvidia, anyone Tech Insights buys the device, slices open the chip under an electron microscope, and publishes exactly what they find. No press releases, no marketing language, just measurements. In December 2025, Tech Insights sliced open a chip inside Huawei's Mate 80 Pro Max smartphone. The chip was a high-silicon Kirin 9030 processor made by SMIC, China's largest and most important semiconductor foundry. What Tech Insights found inside that chip is why you are watching this video. SMIC had produced the Kirin 9030 on a process node they call N+3. That node, confirmed by a third-party lab under an electron microscope, achieved a minimum metal pitch of 32.5 nanometers. That number is smaller than the metal pitch of Intel's latest 18A process node, a Chinese foundry that has been under US export restrictions since 2020, cut off from the most advanced lithography equipment on Earth. Just printed wiring denser than Intel's current generation production process. Without EUV. Without ASML's most advanced machines. Using equipment that ASML itself considers a generation behind what the task required. This is how they did it, and what it means for the most important technology race of our era. If stories like this are exactly why you come to Forgefront, subscribe before we get into the details. Hit the bell too, this story is moving fast, and the next chapter is already being written. To understand what SMIC just pulled off, you need to understand the specific wall they were supposed to be stopped by. Because the wall was not a policy decision, it was physics. When you manufacture a semiconductor chip, you are essentially printing a map. A map of billions of microscopic switches transistors drawn in precise patterns on a piece of silicon. Those patterns are so small, the lines connecting them are thinner than a strand of DNA. To print at that scale, you use light. And this is where the physics problem starts. Light has a wavelength. You cannot use light to print a feature smaller than the light's own wavelength. It is a fundamental rule, like trying to draw a line thinner than your brush. The physics simply do not allow it. The standard lithography machines that SMIC has access to, the kind ASML, has been selling for decades, and that China stockpiled before the export restrictions fully landed, use deep ultraviolet light at 193 nanometers. 193 nanometers. The features on a modern AI chip need to be 30 nanometers wide or less. The math does not work. ASML solved this problem with extreme ultraviolet lithography, EUV. Their machines generate light at 13.5 nanometers, 14 times shorter than DUV, by firing a laser 50,000 times per second at droplets of molten tin falling through a vacuum. The plasma from those collisions emits EUV photons, which are then reflected and focused by mirrors polished to within a fraction of a single atom. These machines cost up to $400 million each. They take 3 cargo aircraft to ship. They are assembled by a team of engineers over weeks. China cannot buy them. ASML is Dutch. Under pressure from the United States and its own government, the Netherlands has not approved any EUV export licenses to China since 2019. Every EUV machine ASML has ever sold to a Chinese customer has been blocked. And without EUV, the conventional wisdom said there was a hard floor somewhere around 7 nanometers below, which China simply could not go. SMIC went below it. And they did it with a technique that the semiconductor industry had never seen used this aggressively at this scale under these constraints. The technique is called SAQP, Self-Aligned Quadruple Patterning. The name is technical, but the concept is a form of engineering brute force that becomes almost elegant when you understand what is actually happening. Here is the core problem. You have a machine that can only print lines 80 nanometers apart. You need lines that are 20 nanometers apart. How do you bridge that gap without a better machine? You do not print the final lines directly. You print a temporary structure first, a series of columns called mandrels. Then you deposit a thin film of material over those mandrels. Then you etch away the film from every flat surface, leaving only the film that clung to the sides of the mandrel's tiny walls, called spacers. Then you remove the original mandrels entirely. You are left with only the spacers. What you have just done is self-aligned double patterning SAQP. One lithography exposure produced two sets of features, because each mandrel left two spacers. You have doubled your pattern density without printing anything new. SAQP does this twice. Take the spacers from the first cycle and use them as new mandrels. Deposit another film, etch it back, and remove the spacers. You now have 4 features for every one that the original exposure printed. Quadruple the density from a single lithography pass. This is how SMIC printed a 32.5 nanometer metal pitch with a machine that operates at 193 nanometers. The math works because SAQP is not cheating physics, it is navigating around it. Each individual lithography exposure still obeys the rules, but by using the results of each exposure to generate the next layer of features without another exposure. SMIC multiplied the resolution of its existing equipment by a factor of 4. The engineering required to do this at a production scale is not trivial. Every additional step is another opportunity for a defect. Every deposition and etch cycle introduces another layer of potential misalignment. The spacers from the second cycle must sit in exactly the right position relative to the spacers from the first cycle, and the tolerance for error is measured in single-digit nanometers across a wafer roughly the size of your palm. SMIC has been working on these techniques since before the export restrictions landed. What TechInsights found in the Kirin 9030 is the production result of years of incremental refinement under extraordinary pressure. Now let us be precise about what the TechInsights measurement actually confirms and what it does not, because the semiconductor industry has spent the past several months debating both with unusual intensity. What TechInsights confirmed, SMIC's N+3 process achieves a minimum metal pitch of 32.5 nanometers. That is a real measurement, made on a real chip by a respected independent lab. It is smaller than the minimum metal pitch of Intel's current 18A process. That is a fact. What TechInsights also said, N+3 remains significantly less scaled than the real 5nm processes from TSMC and Samsung in absolute terms. The transistor density on N+3 matches what TSMC was achieving on its N6 process, a 6nm class node, not a true 5nm. SemiAnalysis, another respected firm that ran its own measurements, said the same thing. The node sits between 7 and 5 nanometers, not at 5. So when news headlines said SMIC achieves 5 nanometer production, the technically precise version is SMIC achieved a process node that beats some 5 nanometer benchmarks in wiring density, but falls short of true 5 nanometer transistor density, sits between the industry's 6 nanometer and 5 nanometer tier, and was accomplished using SAQP patterning applied more aggressively than any production process seen before it. That is still extraordinary. Let it settle for a moment. Intel, one of the original inventors of modern semiconductor manufacturing, with full access to EUV lithography, with ASML machines sitting in its fabrication halls, With decades of accumulated process expertise, Intel's current production node has a larger minimum metal pitch than what SMIC just printed without any of that equipment. China, operating under an equipment embargo that was specifically designed to prevent this outcome, has produced a chip metric that a leading Western foundry has not yet matched. That is the thing the export control architects did not predict. The story of how SMIC got here is not a story of sudden inspiration. It is a story of systematic accumulation under pressure. SMIC was founded in 2000 in Shanghai. For most of its first decade, it was a trailing-edge foundry making chips on older, larger process nodes that the leading foundries had already left behind. That was the business model. Not a frontrunner, a practical supplier. The first U.S. export restrictions on advanced semiconductor equipment to China began arriving in 2020. In that year, SMIC was added to the entity list, cutting off its access to equipment from American suppliers. More critically, it signaled to ASML and other European and Japanese equipment makers that selling advanced tools to SMIC was politically sensitive. The chilling effect on equipment purchases began immediately. SMIC's response was to push its existing equipment as far as it could go. The N+1 and N+2 process generations SMIC's first and second generation 7nm class nodes were both accomplished with DUV equipment purchased before the tightest restrictions landed. The Kirin 9000S, the chip that shocked the West when it appeared inside a Huawei Mate 60 Pro in 2023 with no announcement, was produced on N+2. That was the moment the world realized SMIC had crossed the 7nm threshold using equipment nobody thought could get there. N+3 is the next step. Same DUV equipment, more aggressive patterning, more process steps per layer, more masks. More opportunities for defects and more engineering work to suppress those defects at every stage. The yield rate is where the real constraint lives, and it is worth spending a moment here because it is the number the headlines usually skip. Yield rate is the percentage of chips produced on a wafer that are actually functional. A chip that processes beautifully on some wafers but fails on 20 or 30% of them is commercially marginal. The cost of manufacturing the failed chips still gets paid. The only revenue comes from the successes. TD Cowen analyst Charles Sankar estimated that SMIC's advanced node yield rates on its most aggressive processes run below 20% at certain points in development, far below the 70 to 80% that TSMC achieves at mature production scale on comparable nodes. SMIC's yield rates on N+3 are not publicly confirmed. What is confirmed is that the Kirin 9030 is shipping inside consumer devices at scale, which means yield is good enough for production, not just laboratory demonstration. The floor has been cleared. The question of how far the ceiling goes from here is a different calculation. What does this mean for AI chips specifically? Because the Kirin 9030 is a smartphone processor. The Ascend series, the chips that are replacing NVIDIA inside China's data centers, currently runs on N+2, the 7nm class node. Getting the Ascend family to N+3 or beyond is the next objective, and it is where the stakes for the global AI race are highest. There is a direct relationship between process node advancement and AI chip performance. Moving from 7nm to 5nm allows more transistors in the same chip area. More transistors means more compute units. More compute units mean faster matrix multiplication, which is the mathematical operation that underlies almost every AI model training and inference operation. A 5nm class Ascend chip would not just be incrementally better, it would be a qualitative shift in what Huawei can offer Chinese AI developers who have no access to NVIDIA. In December 2025, the same month, Tech Insights confirmed the N+3 achievement SMIC, and Alibaba announced a partnership to develop a 5-nanometer chip customized specifically for AI inference workloads. Alibaba's cloud division is one of China's largest AI chip consumers. The fact that Alibaba is now partnering with SMIC on a custom 5-nanometer class AI chip, rather than waiting for NVIDIA's export situation to resolve itself, tells you everything about the direction Chinese AI infrastructure is heading. SMIC is also actively testing equipment from domestic suppliers to reduce its dependence on the ASML machines it currently uses. This includes test runs on the 28-nanometer domestic immersion DUV machines produced by Yuliangsheng, the company we covered in the ASML video that started this conversation. The goal is not to replace ASML entirely in the short term. The goal is to establish a domestic supply chain so that when the equipment SMIC currently operates reaches end of life, there are Chinese alternatives in production that can fill the gap. And on the EUV front, the technology that is genuinely needed for 5 nanometers and below in conventional manufacturing China has a parallel program running. The Harbin Institute of Technology has developed a domestic laser-induced discharge plasma EUV light source that achieved power levels between 100 and 150 watts in mid-2025. ASML's production systems require more than 250 watts for high-volume manufacturing. China is below the threshold, but crossing from zero EUV capability to a working prototype with measurable power output is the kind of milestone that separates a paper program from a physical one. The machine exists. It produces EUV photons. It has exposed silicon. The next chapter of this program is already being written. Here is where the analysis needs to hold two things in mind at once, because this story gets misread in both directions. And both misreadings miss something important. Misreading 1, SMIC has solved the chip problem, and China is about to match TSMC. It has not. And it is not. N+3 is not a true 5-nanometer process. The transistor density gap relative to TSMC's N5 and N3 is real and substantial. TSMC is currently ramping 2-nanometer production, while SM1C is working to scale 3 nanometers into a viable process, which the company confirmed is in the tape-out phase using gate-all-around transistor architecture and 2-dimensional materials. The process gap between SMIC and the leading edge has not closed. It remains multiple years wide. Misreading 2. The export controls are working and China is effectively contained. They are not, and it is not. A Chinese foundry operating under an equipment embargo for 5 years just produced a chip metric that beats Intel's current production node on minimum metal pitch. The Kirin 9030 is shipping in consumer devices. SMIC is in production on N+3 and developing N+4. Alibaba has commissioned custom AI chips on this process. The foundry is testing domestic equipment to extend its production life. None of this looks like containment. What it looks like if you read the data without a predetermined conclusion is a foundry that has been forced into an engineering problem so specific and so urgent that it has become genuinely world-class at solving it. SAQP applied at this level of aggression has not been done before by anyone. The techniques SMIC and its equipment partner SiCarrier have developed, some of them now patented. Some of them visible only in tear-down measurements represent real intellectual capital that did not exist before the export restrictions created the pressure to develop it. Jensen Huang said it in the context of Huawei's AI chips, but it applies equally here. Anybody who thought that one chess move would somehow cut off their ability to do this is deeply uninformed. The number that anchors this entire story, 32.5 nanometers, deserves one final moment of context, because its significance goes beyond the chip itself. That number was measured by an independent Canadian research firm. It was confirmed by a second analysis from SemiAnalysis. It appeared on a chip inside a consumer device that went on sale inside China with no announcement, no press release, and no fanfare whatsoever. The same pattern as the Mate 60 Pro 2 years earlier. The same pattern as every significant step in China's semiconductor development over the past 6 years. Not announced until it was already shipping, not claimed until it was already confirmed, not celebrated until the electron microscope showed it was real. The Western semiconductor industry spent 30 years building a system in which the most critical manufacturing knowledge was held by a small number of companies in a small number of countries, specifically because that knowledge was assumed to be the irreplaceable choke point. ASML in the Netherlands, TSMC in Taiwan, the equipment suppliers in Japan and Germany. Hold those choke points, and you hold the technology. The logic was sound. The assumption underneath it that China would be unable to engineer its way around the choke points was not. SMIC's N+3 node does not break that system. Not yet. The true frontier 2 nanometers, gate-all-around transistors, high numerical aperture EUV is still years away from anything SMIC can produce. TSMC is ramping 2 nanometer production now. The gap between the leading edge and what SMIC is producing remains measured in years, not months. The containment architecture still holds at the absolute frontier. But what N+3 proves with a measurement under an electron microscope that no press release can contradict is that the choke points are not permanent. That engineering under pressure produces results that comfortable engineering does not. That a foundry told it cannot cross a line will sometimes find a way to approach it from a direction nobody anticipated. The wall was supposed to be at 7 nanometers. SMIC crossed it in 2023 with the Kirin 9000S. The new wall was supposed to be at 5 nanometers. The Kirin 9030 is not past it, but it is closer than the wall's architects projected, arrived faster than the timelines predicted, and was accomplished using a patterning technique nobody in the Western industry had deployed this aggressively at production scale before. The foundry is now building toward 3 nanometers. The tape-out is already running. The domestic EUV program is producing photons in a laboratory in Harbin. The domestic DUV machines from Yuliangxing are being tested in SMIC's production facilities right now, with the explicit goal of keeping its advanced lines operational when the foreign equipment eventually ages out of service. That is not a contained program. That is a program on a trajectory, one that has already surprised its adversaries twice, and is moving toward a third surprise that the electron microscopes will eventually confirm whether anyone announces it or not. Subscribe to Forge Front if you want to follow where that race goes next. The SMIC 3 nanometer tape-out is already underway. The domestic EUV prototype is producing photons. The Yuliangxing DUV machines are being tested in SMIC's facilities right now. And we have one question for the comments, because this community always brings the sharpest analysis on topics like this. Tech Insights confirmed the 32.5 nanometer metal pitch. SemiAnalysis says the transistor density still falls short of the true 5 nanometers. So here is the question. Does the metal pitch number matter more because it determines wiring density in real AI chip designs? Or does transistor density matter more? Which metric are you watching as the real indicator of SMIC's progress? Drop your answer below.